Hi everyone, so in this video we're going to derive an expression for a wheel rolling down a ramp. So if I draw a picture of this, I have a ramp like so, and then there is a sphere or a wheel or whatever, object we're talking about, and it's going to roll down. Now, it's going to accelerate down the ramp, and of course, we are deriving an expression for the acceleration of the center of mass as it rolls down the ramp. And the reason it rolls is because there is friction involved as well. So the first thing that we have to do here is we have to draw a free body diagram of that object. So if I kind of zoom in on the object here, here's where it's touching that ramp. I have the normal force going straight up, force normal. Of course, I have the force of gravity going straight down towards the center of the earth. And then the force of friction is actually going to be acting at the point where it's contacting this object. And so we have to ask ourselves, okay, what direction is that force of friction going to be? Well, if you want to find the direction of the force of friction for something that's rolling, you have to think about what would happen if there was no friction. Now, if there was no friction, this object would just go down the ramp like this. So it would just literally slide right down the ramp. It wouldn't rotate at all. So because of that, this bottom here will tend to go in this direction, just slide right down the ramp. So since the bottom is going to tend to go down the ramp, then the force of friction has to be up the ramp in order to make that object actually catch and then rotate as it slides down the ramp. Okay? So that's what our free body diagram looks like. Now, of course, we have to split up this force of gravity into X and Y components. So we end up getting, and I'm just going to erase this and just draw it right onto here. We end up getting force of gravity in the X direction, and then, of course, force of gravity in the Y direction. Okay? So if we're going to write an expression now for the acceleration of the center of mass, what we end up getting here is the force of gravity in the X direction minus the force of friction is equal to mass times acceleration, where that force of gravity in the X direction and the force of friction are those two forces that make up the net force that are causing the acceleration down the ramp. Now, force of gravity in the X direction, we know that that's just the force of gravity times the sine of theta. We've talked about that a lot in class. So if you don't know why we use the sine of theta, then please ask me in class or review those videos where we talked about objects on inclines. So we get force of gravity times the sine of theta minus the force of friction equals mass times acceleration. Of course, to reiterate, this right here is our theta, so that's force of gravity times the sine of that angle of the ramp. And then we know force of gravity is also mass times acceleration of gravity, the mass of the object times the acceleration of gravity on Earth in this case. Now let's talk about the force of friction a little bit. So usually we plug in mu times the normal force for the force of friction here. But what's happening here is this force of friction is what's causing that object to rotate. So really what's happening is the force of friction is causing a torque on the object. So because of that, what we want to do here is we want to look at the torque equation in order to get an expression for the force of friction. So we know torque on the object to cause it to rotate down that incline is going to be equal to the moment arm R, which in this case is the radius of our object, times the force that's causing the torque, which in this case is the force of friction. And then it's going to be equal to the sine of theta. That's our equation for moment arm. But of course, if we're looking at that theta, this is our moment arm R, our radius. And then this is the force. So that sine right here is the angle right there is 90 degrees. And sine of 90 degrees is just 1. So here, what we can get is just, we can erase that sine of theta because again, that is just going to be 1 right there because it's the sine of 90. Okay, so what we end up getting for torque is the radius of that object multiplied by the force of friction. Now, we also know that torque is equal to our rotational inertia times the angular acceleration, because that is our Newton's second law equation for torque. And so now we can set these things equal to each other. So what we end up getting here is the radius of the object times the force of friction is equal to the rotational inertia multiplied by the angular acceleration. And then, of course, we are solving for the acceleration of the center of mass. So we're solving for linear acceleration here. So because of that, what we want to do is we want to plug in an expression for angular acceleration that relates it to linear acceleration. So we get angular acceleration equals linear acceleration times radius. We're then going to plug that in for our angular acceleration there. And we end up getting RF of friction equals I, our rotational inertia, times acceleration divided by radius. So now solving for the force of friction here, we get force of friction equals rotational inertia times acceleration divided by r squared. And then we're going to take this whole thing and then plug it in for our force of friction in this equation up here. So what we end up getting is force of gravity, which is m times g, times the sine of the angle of incline minus the force of friction, which we just got an expression for, equals mass times acceleration. Of course, again, we're solving for acceleration here, so I'm going to add that IA over r squared to both sides. And then I'm going to factor out an A. And then divide both sides by this quantity m plus rotational inertia I over r squared to get acceleration by itself. So we end up getting acceleration is equal to mg sine theta divided by m plus rotational inertia over r squared. Now the book actually divides everything here by m just to make it a little bit more pretty. So if we divide every single term by m, we end up getting an expression that looks like this. Acceleration is equal to g sine theta divided by 1 plus I over mr squared. The reason that the book does this is because not only does it make it look a little bit prettier, but also when we plug in rotational inertia, if we get like this is the rotational inertia of a disk, that I would be 1/2 mr squared, which makes that calculation a little bit easy because mr squared just cancels out. Same thing with like if it's a hoop, then it would be mr squared over mr squared, which is just 1, which then makes the denominator just 1 plus 1. So it just makes our calculation a little bit more simple. Now, another thing to note is that the book also has a negative in front of this term right here. So if you look at, this is the equation from the book, we have a negative right here. The reason for that is just that that's the negative direction in the picture that they drew, but I just called that positive, so I don't have a negative in front of mine. So as long as you keep your signs consistent, it's not a huge deal. So this is the equation that we end up getting for our acceleration of a wheel or an object that has a rotational inertia rolling down a ramp. Of course, you can derive this yourself if you're asked for the acceleration, but if you want an equation for this, you can use this one. Or if you're asked to derive it, this is how you derive it when you're doing these problems.